Welcome. We would like to present an experimental software for 3D assembly tolerance design and analysis called Gepard. Gepard is a Russian acronym for Geometric Design and Analysis for Tolerancing. Gepard is being developed in the 3D Tolerancing Research Laboratory of the National Research Irkutsk State Technical University. Gepard system enables the comprehensive three-dimensional analysis of tolerance stack-ups involving all the types of dimensional and geometric variations in any combination. Gepard system allows sharing product geometry data through the step format and can be used in the context of the integrated informational environment. After importing the assembly from any third-party CAD system into Gepard, it is possible to assign all necessary tolerances. Gepard enables us to evaluate assemblability to identify some crucial assembly features influencing directly the product functionality and to optimize the tolerance allocation. A current example shows a movable part of a mold where some tolerances are assigned. We can see the red zone on the accuracy plot for one of the shaft hole joints. It means there are intersections for the shaft hole surfaces in some locations, so assembly is unsuccessful. There is a cross-section of the joint shown in the upper left corner. Once the tolerance analysis is launched, the system generates a clearance and interference values table. Also, an accuracy graph plots the results from the analysis. With this information in hand, a designer can judge whether the selected tolerance scheme satisfies assembly functional requirements. Assembly is successful if the accuracy graph is green completely. Otherwise, a designer should change the selected tolerance scheme or reallocate tolerances. Gepard is based on the novel approach to the assembly modeling. It enables a part and assembly geometry taking into account dimensional and geometric tolerances to be represented in a general way and allows analyzation assemblability at the early design stage. The novel approach is based on three theories: fundamental forms theory, quaternions theory, and configuration spaces theory. We have identified the relationships between these theories and have investigated the possibility of using them together to represent the assembly geometric elements interaction. So, we have obtained a powerful mechanism for assembly modeling and the assemblability analysis. Modeling process in Gepard is divided into several stages. First, a nominal assembly model is created. At this stage, an assembly geometric model or subassembly is imported. It has normal sizes and relationships are represented in terms of fundamental forms and quaternions theory. At the second stage, tolerances are specified and parameterized. We have classified tolerances into three groups. Dimensional, orientation, and location tolerances are represented by unit quaternions model as the group of 3D space rotation. Form tolerances are described by variations of fundamental forms coefficients, combined tolerances. As a result, we obtain an assembly configuration model that absorbs the previously created nominal model. Tolerance analysis based on the assembly configurational model uses the body of knowledge of all three above-mentioned mathematical theories. As was stated earlier, we have classified tolerances into three groups. The first group is dimensional, orientation, and location tolerances. For the orientation and location tolerances example, let's look at the assembly case study with perpendicularity and flatness tolerances assigned on relevant surfaces. By default, there are four various positions for these surfaces. We can change the number of variations. For example, let's change the number of configuration space points to 10. Now you can see 10 positions of the surface. There are three types of configuration spaces for orientation and location tolerances. Unit sphere bounded by a circular segment, which axis is the vector n, and the largest deviation angle is the angle gamma. Arc of the unit circle with the axis n and the angle 2 gamma. Circle with diameter of delta and centered at the origin. In the tables presented, you can see all Gepard tolerance models. The two tables show orientation and location tolerance representation as follow. Thus, using the quaternion-based transformation formula for marked frame transformation, for every point of the configuration space we can obtain some position of the surface marked frame in 3D. Some formulas for basic transformation are shown in the right column of the tables. So for some perimeter values corresponding to some allowable variation of the surface location, we can find different positions of this surface marked frame within a specified tolerance, and hence the position of the surface is fully defined in 3 dimensions. Next, we consider the second tolerance group, form tolerances. Examples of form tolerances are special cases of deviation from flatness tolerance, the convexity and concavity, and the deviation of the profile of longitudinal section of a cylindrical surface, namely its special cases, barrel shape, saddle shape, conset A. In this case, with some assigned tolerances in mind, some allowable surface locations represent in terms of variations of coefficients of the first and second fundamental forms. In this table, we can see some types of form tolerances in the relevant configuration spaces, as well as the transformation formula for coefficients of the fundamental forms of surfaces in the points of configuration spaces. Thus, for different points of the configuration space corresponding to some form of allowable variation of the surface, we obtain different values of the coefficients for quadratic forms of the surface within a specified tolerance, and hence the position of the surface is fully defined in 3D. Sometimes there is a need to assign different types of tolerances for some surfaces. We call it combined tolerances. In this example, some tolerances assigned for one of the holes size tolerance for diameter, axis perpendicularity tolerance, and axis position tolerance. If the diameter tolerance is considered separately, there are 2 points of the configuration space by default, so there are 2 hole surface locations. For the axis positional tolerance, there are 4 points of the configuration space by default. Hence, there are 4 different hole surface locations. Then, when a combination of 2 tolerances is considered, we get 8 different hole surface locations. Similarly, adding a third tolerance in this tolerance composition, axis perpendicularity tolerance, with 4 points of the configuration space, we obtain 32 different allowable hole surface locations. Thus, the configuration space of the surface is a direct product of configuration spaces for its tolerances assigned. For the representation of the entire assembly model, one should consider first the configuration space of every tolerance. Then, as shown above, the configuration space of the surface is a direct product of the configuration spaces of tolerances assigned on this surface. The configuration space of a component is a direct product of the configuration spaces of tolerances assigned on this component, and so on. The last would be the assembly configurational space. To assign tolerances on a surface, a designer selects the surface and datum, the type of tolerance, and its minimum and maximum values. Further, the system enables a list of configuration space points by default. Users can edit them at any time. Tolerance perimeter dialog box indicates tolerances, and their values are specified. So, for one of the holes, first we have assigned position tolerance, then size tolerance for hole diameter. Similarly, one can assign tolerances to other surfaces of the part. For parts assembling, one needs to have models of 2 components imported into Gepard To create an assembly model, a designer specifies for the components both the relevant mating surfaces and their relations in the mating perimeter dialog box. It is important to assign mating relations in such a way to restrict components' degrees of freedom completely, so assembly is unambiguous. By adding new components, an assembly graph is forming. It contains full assembly information, including tolerances and mating relations. Now that the assembly configuration model is finished, we can proceed to an assemblability analysis. After the assemblability analysis is completed, for every point of configuration space, the results are outputted in an assemblability analysis dialog box. To view the results for the relevant point of configuration space on 3D assembly model directly, one needs to click on this point in the assemblability analysis dialog box. By selecting a surface on the 3D assembly model, one can view the analysis results on the accuracy plot with clearance and interface values in every point of the configuration space. Also, one can view the maximum clearance and interference values in the assemblability analysis dialog box. Key features: CAD integration. Step: 3D tolerance analysis, worst case. Dimensional, orientation, location, form, combined tolerances. Universal mathematical model for tolerance representation and analysis. We welcome partners and investors.